I'm starting to use this phrase, engineered intelligence, because to me, what engineers do is build things with building blocks. They design complex systems from building blocks. And I think that artificial intelligence should be that way too.
You're listening to Augmented Ops, where manufacturing meets innovation. We highlight the transformative ideas and technologies shaping the front lines of operations, helping you stay ahead of the curve in the rapidly evolving world of industrial tech. Here's your host, Natan Linder, CEO and co-founder of Tulip, the frontline operations platform.
Welcome to Augmented Ops. We have Kence Anderson, who is the CEO of Composable. Hi, Kence.
How you doing, Natan? Great to be here.
Great to have you. This is a specifically exciting episode. I think we haven't done something like this in a while, where we have a founder who is relatively early in the journey coming and talking about what they're doing at the moment of time. I always find this fascinating because not only it shows us, hey, this is stuff people are working on right now, meaning they believe in it. They found some other people who believe in it, and they're going to build it, and the rest follows. But maybe before we jump into that, tell us a little bit about yourself.
Oh, of course, and thanks for the focus. I love origin stories too, so I think that is the exciting part. But my background is mechanical engineering by education, but I've been in startups my whole career. This is the 8th startup that I've been a part of, and all horizontal platforms. Mm-hmm. For the last 7 years, I've been focused exclusively on industrial autonomy or autonomous systems for industry, or now folks, including me, are calling it things like intelligent autonomous agents. Mm-hmm. And that was at a startup company called Bonsai, mm-hmm. which was acquired by Microsoft, and 5 years at Microsoft where I worked on autonomous AI adoption. And what was interesting for me was really traveling all around the world, going to every kind of factory, chemical plant, mine, manufacturing center, warehouse, oil refinery, steel mill, you name it, mm-hmm. trying to understand how to apply AI to decision-making, to actual industrial decision-making. I'm talking about like the control systems, the optimization systems. I think
closing the loop.
Closing the loop. For years and maybe decades, we've been talking about how to apply ML to other parts of the decision-making, maybe segments of the decision-making process, like how I can use a prediction, how I can use analytics. And honestly, sometimes the hype has kind of sidetracked us and got us thinking that that's going to provide some largely material part of the decision-making process, but it doesn't. A prediction in a factory, for example, is only useful in that it helps you make a better decision. Mm-hmm. So it was going around and talking to executives all the way down to plant floors, like a lot of hard hats and a lot of steel-toed boots and all that. And I personally designed over 200 of these kind of autonomous AI systems.
So let's step back for a second, because you wrote a book, Designing Autonomous AI, a guide for machine teaching. First of all, congrats. Books are cool and hard to produce, I've learned personally.
Yes, and yes.
And I also think there's a lot in the title. And so what's interesting in the title of your book is people typically talk about machine learning. They don't talk about machine teaching.
Yes. So the first part of this title, autonomous AI, and what I mean by autonomous AI or intelligent autonomous agents is for decision-making, certainly industrial decision-making, but this could also apply to other kinds of decision-making. I would go to these factories and I'd say, well, what is this person doing here? You have an automation system. And they'd say, oh, well, and then they'd start listing off what I now think of as qualities of more human-like decision-making that automation does not possess. Things like perception. Where an operator would say, oh, no, you can't be an expert at this unless you can see this color change or you can hear the sound the tool makes. And they would talk to me about other things like adaptability, or us controls people call it like robust control, mm-hmm. or strategy. And so there's all these different qualities of more human-like decision-making. And that's what I mean by autonomous, even though a lot of times it's assisting a human.
Mm-hmm. It'd be great if you pick a couple examples of the 200 systems you deployed out there, because I think more and more we're exposed to AI in daily consumer-prosumer life, yes. with ChatGPT and whatnot. And this is a bit of sort of my MIT roots, if you like. We always talked about the notion of disappearing AI, where when the computer algorithm just works and produces predictable good results. We take it out of the AI bucket and we say, well, that's just like a solution to the problem. And one of the key example of that has been very close to my heart, because my PhD advisor, Professor Patty Maas out of the Media Lab, is well known for software agents. Like that was her key work and a recommendation system at the time. And she gave the examples of, you know, how you go to Amazon now and it's like, oh, people who bought this also bought that. And I don't think anybody thinks about that as AI today. They just think about, oh, well, the internet does that.
Absolutely.
But back in 1987 or whenever that published, that was cutting edge recommendation systems.
And that was AI. And same thing happened with expert systems.
Yeah,
where,
exactly.
You know, expert systems with AI, and then it was, you know, declared dead, if you will, you know, when it didn't live up to all the hype. Yeah. But that's kind of how AI research tends to work. Expert systems in the 80s were going to replace doctors, you know, going to replace lawyers, you know, maybe be conscious, you know, implemented on robots, declared dead, but then widely adopted and used in banking and engineering. And folks don't even consider it AI anymore. It's just a system that works, right? So to your question about why machine teaching, the answer is really simple. If machines can learn, then you should teach them something.
Yeah.
So when my son, for example, he's 11 years now, but when he was first learning to play basketball, I was teaching him how to play basketball a little bit when he was, 4 and 5. I didn't like throw him away and get a new son when he didn't learn something properly. I just taught him. I taught him a new skill.
You just upgrade the firmware, I guess.
Yeah, exactly.
That's better.
Exactly. Yeah, it does upgrade over time, but at that point, I didn't have the option, right? So I think we're moving from a very algorithmic paradigm, which I think we've been in ever since Turing. So pre-Turing, it was, well, you need a different machine if you want intelligence for a different task. Like literally, that's like what the IBM voting machine is, or what an automaton is. It's a machine that has the intelligence built into the mechanics of it, whether it's pneumatics or whatever it was. Mm-hmm. Once software came along, then it's a new algorithm. In order to get new intelligence, you need a new algorithm. But if you have a learning algorithm, you don't need a new algorithm. You need to teach it something. So I believe that expertise is a knowledge graph of skills practice to competence. And I'll give you an industrial example in a minute, but let's just take a colloquial example. Yep. Imagine like flying a drone.
Yeah.
Like takeoff is a completely different concern than landing. Completely different skill.
Or turning.
That's right. And then you might have to avoid obstacles along the way, a bird or something. And so you have this knowledge graph of skills, and expertise is learning when to activate those skills and how to blend them together and improvise from them. That's what football plays are. That's what chess strategies are. And certainly when I went into factories, folks would fill whiteboards with lists of these skills and strategies that you have to learn how to navigate. So I started thinking about, it's like this kind of knowledge graph. It's this graph, and it's a acyclic graph, but it's a graph of these skills. And that's what teaching is, though, isn't it? Teaching is drawing a box around promising areas of practice. So when you're becoming a pilot, which I'm not, then there are times when you're practicing takeoff and there are times when you're practicing landing. You're not practicing the whole thing all at the same time.
Until some point that there's an integration.
Until some level. And
you take your solo flight.
That would be part of the curriculum.
I guess a solo flight is composed, right, from the theory of aviation and why do you have lift, the physics, the mechanical systems, and then after all those blocks are there, you can do it on your own, which is another level of learning and skill.
I would say we were actually just discussing 3 levels. The first level is the level of the actions themselves, the rudder, the ailerons, and the radio, etc.
Yeah.
The second is the level of the skill, and the third level is the level of the task. And so at the first level, and this is part of what I talk about in the book, is there is a theory of expertise development, of skill development by the Dreyfus brothers. They were innovators in the symbolic age of AI, and they developed this skill acquisition framework. And I modified it, added to it, kind of built my own skill acquisition framework for AI. But when you first start learning something, you're thinking at the lower action level. You're thinking, what do I do with the ailerons? What do I do with the thing? Eventually, you abstract a level and you're thinking about skills. That's what like opening strategies are, opening sequences are in chess, or mating strategies. You're not actually thinking about each individual move. You're thinking, which strategy should I use? And then you've practiced each of those skills or strategies so much that you don't think about the underlying. Then you compose into the task.
Let's dive deeper a bit. You named your company Composable. When I was reading your stuff, I was like, okay, this could fit a bank and this could fit a hospital. This could fit a school. There's no place where
100%.
you can have an organization of people, some level of complexity, set of tasks, stakeholders. You can apply this strategy. But Composable seems like chose operations. So let's talk about this name Composable. You know, I have a romance with here at Tulip with composability. To anyone who would listen to us, we try and preach like open composable architectures from the IT perspective, but also, you know, composability at the hands of the people who actually do the work. We're clearly operation focused. So, you know, for us, it's like engineers, process engineers, industrial process engineers, safety, lean, all those folks on shop floors, machine shop, wherever, where they can actually do the work with something that is composable. It really means we don't know what they're going to build. We know the type of stuff they're going to build. We know that we're giving them no-code, low-code AI tools to do it, but we're not enforcing a certain data structure. We're proposing one. We're not enforcing one way of building it. We're suggesting how to do it, but still open to what customers need to build. And I think that's done in an architecture that I like to call action-driven architecture. So it's on the nuts and bolts of the pub sub events, you know, if we're kind of nerding out a little bit here, but it's really about how do you create value to a customer? Well, if something's happening now in your operation, you need to take actions, then that's sort of like the point. So that's composability for us. But you run Composable. What's Composable and how do you define it?
So really, Composable is about building blocks, just like you said. And I'm starting to use this phrase, engineered intelligence, because to me, what engineers do is build things with building blocks. Like no complex system anywhere, no engineered system, well-engineered system anywhere is monolithic. If it's complex enough, it's going to have different component pieces and different subsystems. And that's what engineers do. They design complex systems from building blocks. Mm-hmm. And I think that artificial intelligence should be that way too. By the way, our brain is architected that way too. Yeah. Most of the philosophical arguments I hear about whether it's large language models or deep reinforcement learning or whatever are arguments about the algorithm. But what I don't hear many people talking about is the brain is a completely modular architecture that has completely separate concerns where each of those modules does different things in different ways. Like your amygdala and your prefrontal cortex, not only are they different in their function, it's almost like the difference between expert systems and reinforcement learning or memory and some other component in computer architecture. They're completely different modules that function in different ways. Mm-hmm. That's how engineered systems are. I just gave you an example of intelligence, and I'll give you an industrial example. So believe it or not, making Cheetos is difficult. And Cheetos called me up, and I never thought about making Cheetos, but PepsiCo Snack Foods makes Cheetos.
And I mostly think about eating Cheetos.
That's what I think about. That's what I look forward to. Yeah. My son is like addicted to the flaming hot Cheetos right now. And I said, what's hard about this? And they said, first of all, I need to let you know that it takes like 10 to 12 years to become an expert at operating this extruder. So an extruder is this piece of equipment. You can make all sorts of things on extruders, like films for screens, soap, pet food, all sorts of stuff. But you also make Cheetos in an extruder. It's basically a metal tube. Material comes in this case, cornmeal. There's a screw that moves it along. It's under pressure inside, and it's heated up in different sections, which for Cheetos means it gets cooked, which is a very complex process, and then it gets forced out of a slit or an orifice. And that's when it puffs up because of the pressure differential. Mm-hmm. And in order to get it to puff up to the right size, in other words, length, diameter, curl, like they actually measure the curl of it, and the density, how big the bubbles are, you're controlling 25 different things. Every 15 minutes, you're controlling 25 different things. That takes a long time to learn, but that's not even the hardest part. The hardest part is one of the things that matters most is how wet the corn is, and you can't measure it. So there's, an IoT is, just put another sensor in there. Nope. Can't measure the wetness of the corn. It changes as it's stored. It depends on how it was stored, how it was grown, etc. And it's not uniform. Even inside like a corn kernel, for example. So an expert operator, you put in a new batch of corn and they'll go, oh my gosh, this is like super wet corn. And they know that because they're pattern matching between the controls that they're controlling and the way that the output is changing. So the Cheetos start changing in the way they come out and they go, oh yeah, that's really wet corn. So it's deducing. That's one of the more human-like decision-making characteristics. And so long story short, we designed with them an agent that was certified in a pilot plant as an expert operator. Again, it takes like 12 years to learn how to do this. We spent 2 weeks training this thing.
So that bot, let's just call it Cheeto bot, could figure out, and I guess like the way we go about proving viability of any machine learning model or AI model that works in the real world, you kind of test it out with some accuracy metrics or...
Yes, exactly. It was quality metrics. in a variety of different scenarios. So they ran it through a bunch of different scenarios. You imagine wetness of corn and lots of other parameters, and how it behaved in staying within the quality parameters throughout those scenarios. Now, here's where the modularity comes in. We tried deep reinforcement learning by itself, and it was okay, kind of medium expert operator. But we got to the expertise when we interviewed an expert, and the expert said, hey, there's 4 or 5 different skills, just like takeoff and landing are different. There's 4 or 5 different skills for how to manipulate these 25 variables. Mm-hmm. And some of the skills need to go in a sequence in the same way as takeoff and landing. So think about this knowledge graph again of skills. Takeoff and landing must appear in a sequence. There is no landing until you take off.
But back to training the Cheetah bot, because a lot of our listeners would love to train a bot to do whatever, like the bot to make sure my torquing profiles are right, and a bot to make sure that the new batch of trainees I just brought in are performing to the relative level after a couple weeks and not below, or maybe not even faster. And I can imagine more and more bots like that could come up in operation. It's probably a parallel universe to everything you need to do in a factory, which is many human-based operations and many automations and the combination thereof, right? So how did you actually train this Cheetah bot?
So the teaching first, then the training. And this is also part of the answer to the question is, why are we starting in industrial? Like, I've done agents for fraud prevention, commodity trading, financial allocation, all sorts of knowledge work and enterprise tasks that have nothing to do with industrial per se. But the thing about industrial is you have all this expertise. Expertise is previous exploration of a state space. So when Alpha Chess discovered, by playing itself, the 12 most common openings in chess, it's basically discovering expertise we already had. One of the openings that it used consistently was 1,000 years old. So it's playing itself, and it's discovering opening sequences without being taught explicitly that humans have known about forever. Same thing is true in a factory. If you just let the AI just learn on its own without teaching it the things that you already know, then one, the results are inconsistent, the results aren't high quality, and you're spending a bunch of training costs to discover stuff that you already know. So the first thing that I do is I interview the operator. And I say, decompose this task into skills. Like a pilot would say, well, you got to learn how to take off, you got to learn how to land, and how do you orchestrate these skills together? Well, takeoff goes before landing. And the same thing happened in this Cheetos use case. We interviewed an expert, and they said, oh, there's these 5 skills. Here's what they're called. Obviously, can't talk about what they are, but here's what they are, and here's how you sequence them. Some of them appear in a hierarchy. And so I formulated a teaching plan that explicitly taught these 5 skills. So now I have a modular agent that has 5 different modules in it. I decide how they're orchestrated together, and then I decide what algorithms I'm going to use to execute those skills. Because some skills in a safety critical environment might be executed best by a rules-based system, or maybe by a DRL system. And so then when you train it, like with my son with the basketball, he's training on what I've taught him. I've taught him the jump shot. He's not training on the task of basketball at large. He's training on the specific skills, and that's how I guide him through his increase in expertise.
So let me challenge you a little bit. This sounds pretty complex. My question to you is who's the teacher?
Yeah, the teacher is a subject matter expert. So when I go into a steel mill, I don't know much about steel, but they do. Yeah. To an engineer that's making steel, this is not complex.
Yeah, they can talk about this all day long, but I guess if they're the teacher, the result of them applying this methodology, for machine teaching, I think the output of this is a bot or an agent, let's just call it like that. For those people in the shop floor, and I think this is what's most interesting to learn about what you all are doing, is how do you make it easy for the engineers who are not AI experts, right? They didn't spend their careers doing what you're doing. They know a lot about what they're doing, but they don't know what AI unsupervised, supervised technique necessarily looks like, and why does it exist, and all these kind of things. So beautiful. Help us understand that.
So that's the other reason for machine teaching, because it's an abstraction from machine learning. So when you're working with Composabl, you don't need to understand how deep reinforcement learning works.
And how do you guys do that? So I get the idea. And I think we have a parallel sort of existence, when we go to people who are not software. They understand software. We all understand software. You use software. But Most people on the planet just don't write software in general.
Yes.
Or we have the same thing with computer vision. We kind of say the same thing. So we tell them, you hook up the thing to the you hook up a camera,
Exactly.
and then there you select your area of interest, and you tell it, I want to find a hand, and like people go like, oh yeah, I understand. I can tell it to find a hand, and tell it to look for an object, and it knows how to find an object. So that's how we do it. But our output at the end is just software. It's like interactive, UI, without UI type of thing. Your thing is an entity that is running there that needs to be quote unquote connected and like shooting out information to make decisions. And so how does it actually work?
So first, how do you create it? Then how do you connect it? Then how do you explain it? Right.
Yep.
So first, how do you create it? So imagine literally a drag and drop interface where you can go, oh, well, what skills do you want to create? Well, I want to create a landing skill, a takeoff skill.
So you can define that taxonomy of skills that you need.
Define that knowledge graph right there, that taxonomy right there.
That's cool.
Then for each skill, you can say, what are the goals? Because the goal for takeoff is to get in the air. The goal for landing is the exact opposite. Not just to get down.
The goal is not to crash.
Yes, getting down and avoid crashing. And so we have an abstraction system of goals. So people aren't writing like reward functions. They're saying, I want to minimize this. I want to maximize this. I want to avoid these things. I want to maintain things within this range, that kind of thing. And every engineer kind of understands their problem in terms of those kind of abstract goals.
But they know it in the realm of human language. They don't know it necessarily in the realm of abstractions for AI agent to be effective. Do you agree?
Yes, I do agree. So that's why we created our goal abstraction.
Okay.
But you can also create skills and goals in Composable from natural language.
Nice.
So you can say, listen, I want to train an agent to land the SpaceX Starship on its tail. And there's 5 phases of, this is a demo I like to do. There's 5 phases of the landing. And I don't actually know what those 5 phases are. At least I didn't before I did the demo 100 times. I want to define one skill for each of the 5 phases. And the goal is to land safely, avoid crashing, which is defined as, you bring Y position to 0, avoid Y velocities over a certain amount. And we'll call ChatGPT, and ChatGPT will go and it'll research those phases. It'll create those skills, and it'll even create draft goals that I can go in and I can modify, right? So there is this bootstrapping issue where, yes, if you were super skilled and probably knew a lot about AI, you could probably punch in all that into our system or our SDK by hand. But the LLM helps, and the LLM also helps on the explainability side. So imagine inside an agent, you've got these modules that are making decisions. We call that the decision layer. You've got these other modules that are perceiving things. We call that the perception layer. That's your computer vision and your prediction and your clustering and all that. But you've also got assistants. And assistants are communicating with folks in natural language. So without the assistants, you connect the agent up to an HMI and you have to hand roll, exactly what the agent output looks like to the user, whether it's a mobile app or an HMI on a factory machine. But when you have the assistants, you can literally ask the analyst assistant, why the heck is the agent doing this right now? Mm-hmm. And it says, oh, well, according to the standard operating procedures here, look at this text. In these scenarios, you're supposed to do this. I can prove to you that we're in this scenario because here's these 3 charts of the variables, and you can interact with it. You could also interact with like kind of a plant manager assistant and say to it, hey, this equipment is running way too hot. And that plant manager will translate to the decision layer the numerical values and the categories that actually affect the algorithms that are making the decisions. Mm-hmm. You can even pull in information from outside the state space. Imagine like an executive co-pilot who is looking at the Wall Street Journal and political happenings and market watch and saying, oh, we need to increase the throughput of our plant right now.
Or they may be looking, if it's a public company, they might look at the ESG report that everybody gets an email, but no one reads. And then it says, hey, we feel like this value stream has like too much emissions or, I don't know, too much scrap. And we should really watch because our company's goal for ESG is blah, blah, blah. And then it might affect human behavior with just connecting this information. It really falls into, and again, I don't think it's necessarily GPT related, but I'm sure you've seen them, these meta GPT, like bake me a cake. And it would be like, okay, to bake a cake, you need to select the cake type and then you need to do this, that. And like it would start running like multi-thread GPTs.
That's right. And that's what the generative AI is particularly good at.
Yeah.
Analyzing, researching, synthesizing. Like some people are claiming that the large language model could be the entire agent, which could certainly work for some back office tasks, usually repetitive, lower value tasks. But we're talking about super high value super high risk operations that require extreme nuanced decision making. And in that case, you want to use the generative AI for the human interface.
So where do you see this taking root as first core use cases for what you're offering?
Sure. We have 2 Fortune 500 companies that we're working with right now. One is working on a logistics problem.
Mm-hmm.
And it's about scheduling. So most logistics is about scheduling. You know, scheduling a warehouse, scheduling how.
Scheduling is like one of the most open-ended, annoying topics in operations.
And the reason why it's so hard is because, an operations researcher will say, oh, well, we use optimization algorithms. The reason why no one's using optimization
Dynamic
algorithms
scheduling solves all your problems. No doubt.
Exactly. But it's dealing with the stochasticity of demand and the fluctuation of demand, which optimization is horrible at.
Well, I would say it also deals with the optimism of people because we're horrible at forecasting anything.
Right. And we have usually in most cases in real scheduling situations, there's multiple forecasts with different biases. And it's a human being that's reading those forecasts and
optimism is a form of bias. Yeah.
That's it. So that is highly promising. We have many use cases going in kind of scheduling, supply chain and logistics scheduling. The other Fortune 500 company we're working with, it's machine control. It's analogous to an extruder, but a completely different kind of machine that makes completely different kind of things. Very complex, 90 different sensor variables.
Custom machine that makes something, it's not like a CNC machine, say, that is very... Yeah, it could be very sophisticated, but it's a very regular machine, so to speak.
You got it. And very complex in its operation. I think most hand-controlled CNC machines have, 4 or 5 things you're controlling. I mean, this is 60 things that you're controlling in real time.
So your bot or agent would actually close the loop and feed it back all the way to the control.
So in this particular case, it's providing what I call kind of level 1 control, which is decision support opt-in, which is basically saying to the operator a recommendation. Now, it did so well in production testing, the expert operator, and mind you, the expert operator was involved in this teaching process the entire time. So he saw it and taught it more and improved it. And he said, you know what, let's move to the next level. Let's have it opt out. Let's have it do what it wants to do unless I override it. And then the next level is, complete closed loop. But I got to tell you, in the majority of the cases, folks don't actually want completely closed loop because they want it to train the people. In most cases, you have 10% of operators that are expert and everyone else performs significantly less effectively. And so they're more interested in using it to improve people's performance than they are in replacing people or automating.
Yeah. And I'm guessing that at some point for your second example, you could prove it with the standard statistical process control techniques. That at least over a certain amount of time that this thing is running as compared to human state, let's just call it the human state and the bot state.
That's right. Human state or some other form of automation, yes.
Well, that's awesome. I want to switch gears because, this year Tulip is turning 10 in a few months. And it's been quite a journey for us, growing a platform like Tulip. And it's always exciting to meet someone who's earlier in the journey and venturing into operation with new exciting technology where you could have chosen any sort of operation. So we heard why you're doing it, but maybe you can share, how does it feel like to build a startup in operation, for industrial use cases nowadays?
It is exciting, but mindset is important and curiosity is the key. I think that so many tech companies have failed, big and small, condescending to and misunderstanding operations. I've been to plants where people say, oh, Kence, thank you so much for not condescending to me. And these people are PhDs in control theory and mathematical optimization. I'm like, what are you talking about?
Yeah.
They go, some tech companies coming in here and telling me all they need is my data and they'll hand it to a data scientist and they'll replace all of us. And of course, that's folly. So it takes a lot of curiosity to realize that not only do I not understand this specific use case, what do I know about making steel and making soap and making Cheetos and, and moving packages? Nothing.
Before Microsoft, did you spend a bunch of time in operation? I mean, have you been around production lines?
Not a bunch of time, but I was able to work for Ford in manufacturing for a little while.
Okay.
So I've seen it. I've been in plants before and I've seen the scrap piles, I've seen the, what yield looks like and I've seen the testing. And so I think my background as an engineer in general, but a mechanical engineer and working in manufacturing and design was super helpful. You have to be really willing to learn because operations works really differently than IT does. And physical things work really differently than software. For example, you take something like developer evangelism, like how you get people to use your product. If it's a software product, you say, oh, you open source it and people will tinker with it. But like in these industrial environments, like the thing that would be tinkered with cost $100 million and it could kill you. So there's just a completely different like way you have to.
Or I keep thinking sometimes about our life science customers and like when they say, oh, we ran a couple of batches, and like every time they say a couple, it's like only a couple of $1 million for like, a few bags of material that they produce out of it, the product. And it's so much responsibility.
It's so much responsibility. So it produces a different mindset. Just to add to your example, oil exploration, a test well could cost $30 million. The well that is just to test whether it's a place you want to explore. So yes, it's a very different mindset. Engineers have a different mindset because of it. But to me, I find that exciting. So to me, there's a whole new audience to quote unquote evangelize or get to adopt technology that think very differently than software engineers. And by the way, there's an order of magnitude, 10 times more engineers in industry, your process and controls and manufacturing and chemical and mechanical engineers, than there are software engineers on the planet. So I find that fascinating, but it's super risky because there's a million ways to get it wrong. Like there's templates and plans for how to evangelize software of different kinds, but not as much for OT.
Well, the scalability function is different when your product is requiring you to spend face time with an expert and understanding the physical properties of a process and all that kind of stuff. So what's next for Composabl? So you guys are on month 18.
Yes.
What's the next 18 month? What are you focused on? What is Composabl looking for? And what is your call out to community? In Tulip, we're very focused on the ecosystem. We don't think that we can create enough value for the customers alone. I
really appreciate that question.
That's really an arrogant way of thinking about it. Because you said about, they come there and condescend them and whatever. But
that's leadership. I understand. That's leadership.
It's how we need to treat them as our stakeholders. And so what's next for Composabl?
Composabl has a product in market. We have some customers using it to solve some really high value problems. Next is enabling an ecosystem of system integrators and customers themselves that are solving more problems at a greater scale, coming up with some kind of clusters of common use cases and value chains that you can solve in an industrial and even broader in enterprise. What that means for the community for us is we are a composable platform, so there's integrations to be done. The first is integrations with partners that provide data for training agents, historian companies, things like that. The second is partnerships that plug in specialized algorithms, MPC controllers, real-time optimizers, quantum optimizers. There's all sorts of things you want to put in an agent, assistants and co-pilots and foundation models. And then the third is technology partnerships that enable us to push an agent to very valuable places, ERP systems where they can make decisions, MES systems and control layers for down to specific machines and specific form factors of machines and things like that. So it's really the next 18 months for us is about building the integrations in the ecosystem.
Do you see a world where some company, let's just say in the automotive space, trained humans to weld? And so they created the conceptual model and a skill of the master welder that kind of helps you train the welder. And they might exchange it because welding also happens in the building and construction industry, which is, welding is welding, but it's not the same. Do you see a world where Composabl becomes a platform to exchange those kinds of models and knowledge?
I do. One venture capitalist called our platform an operating system for skills. And right now, these skills are specific to a task, but we're already starting to experiment with and see with foundation models and transfer learning and other things, the ability to transfer skills to similar. Now, I'm not talking about AGI, like, washing dishes and working in a factory, but I am talking about this fuzzy boundary where, like the example you gave, where you can transfer a welding skill from one factory to a completely different type of factory. I do see that in the next few years.
Well, that's a great and bright future, and we'd love to see you in our ecosystem. I think that's all the time we've got. So thanks for coming on Augmented Ops and sharing a bit. I hope to see you soon and hear great updates about your progress and as you guys kind of launch.
Thanks so much. I really appreciate you inviting me, and it's been great to be here. Really engaging conversation.
Thank you so much.
Thank you for listening to the Augmented Ops podcast from Tulip Interfaces. We hope you found this week's episode informative and inspiring. You can find the show on LinkedIn and YouTube, or at tulip.co/podcast. If you enjoyed this episode, please leave us a rating or review on iTunes or wherever you listen to your podcasts. Until next time.